According to Theorem 1 in section 72, the series 1 are Taylor series. Here and here are Taylor series. So we are now compute the Taylor series of the product of f of g and g of g by just applying the Taylor theorem. We can compute the coefficient of this series and actually this series is the Taylor series expansion for f of g and f of g times g of g in the powers of g negative g naught by theorem 1. So we just apply the formula of Taylor expansion to compute a Cn given by this nth derivative of large f. Here large f is defined by the product of f of g and g of g. So Cn is computed by this form as derivative of large f at g naught divided by n factorial here. Let's compute the first few coefficient of large fg, which is the product of small f of g times g of g by differentiating it. The first, we have this value, small f of g naught times g of g naught for large f g naught. So c sub 0 is computed by this. Zeroth derivative of large f, which means original function large f at g naught divided by 0 factorial here, then which is a small f of g naught times g of g naught, which is computed by this form. When we insert g naught for g here, then we get this a sub 0 here, because from this expression we get this a0 plus a1 times g negative g naught. Then we get a2 times g negative g naught to the squared here. So here when we insert g0 here for g, then these terms are getting 0, and then we get this a0 by argument of symmetry argument. For the case of g of g, we have the b sub 0 for g of g0. Next, we move to compute c sub 1. To get this, we first compute the first derivative of f at g naught, which is computed by this formula by product differentiation rule for the product function. So c sub 1 is computed by this, the first derivative of large f at g naught divided by 1 factorial here, and this part is replaced by this, and then compute from this series for f of g and g of g. In this case, f of g naught is a0. We have already computed previously. Here we get this. And g prime g naught is computed by this formula. Because we have this form, Taylor series expansion for g of g, we differentiating both sides, then we get the first derivative of this function for the expansion of on the right hand side here. And so we make a general rule for this, and then eventually we get this result here. So we just insert n1 for n here. Then here is sorry, there's a typo here. Here is n should be k. Then we insert 1 for n here. Then we for the k is 0. Then we get this 0 factorial, 1 factorial over 0 factorial times here n is 1 and k is 0. Then b1 times g naught to the power of in this case 0. Okay, so the constant coefficient is b1. Okay, so for this we replace it. So a0 times b1 for the first term here, plus for the first derivative small f at g0 is computed from this formula, and by using a similar argument for this value we get a1, and g of g0 is b sub 0, which we have already computed previous here. So c1 is a0 b1 plus a1 times b0. And next move to compute c2 here. We need to compute a second derivative of large f here, and using a similar computation by using this form expansion series, power series here, and the nth derivative of this f of g and g of g here. Then we get this for c sub 2, a0 times b2 plus a1 times b1 plus a2 times b0. We computed first three coefficients in series 2 here. In this way, we could compute every coefficient for this function. The general expression for any coefficient Cn is easily obtained by referring to Leibniz's rule, which is still with exercise 7. So it is given by this expression 3. Fg times g of g. So nth derivative of this function is given by this formula. Summation k is 0 to n to k times k's derivative of f times n negative k derivative of g Here n goes to from 1 to infinity and is non-negative positive integer, where n to k is defined by this n factorial divided by k factorial times n negative k factorial. Here k from 0, 1 to n for the nth derivative of the product of two differentiable functions. As usual, we assume that zeroth derivative is defined by the original function small f of g, and 0 factorial is equal to 1. Evidently, c sub n is given by this. By using this effect, summation k is 0 to n. The case derivative of g0 divided by k factorial times n negative k derivative of g of g0 divided by n negative k factorial. This term is equal to this term. Summation k is 0 to n a sub k times b sub n negative k. Let's check it, the formula just we compute here. Especially when n is 1, the product rule for derivative with two differentiable functions we have learned in the previous section. The product of f of g, when we differentiate in this function product, I mean that we get this f prime times g of g plus f of g, g times g, which is exactly same to summation k is 0 to 1, 1 choose k, k's derivative of f times 1 negative k derivative of g. Here there are two terms. First, when k is 0, we get this 1 0, 1 choose 0, f of g, and g, first derivative of g, and plus k is 1, in the case of k is 1, we get this 1 choose 1, once the first derivative of f of g times g function, so which is exactly the same here. So the expansion 2 can be written like this: fg times g of g a0 b0 plus a0 b a0 times b1 plus a1 times b0 times g negative g0, and the second order terms here, the coefficient is given by this a sub 0 b times b2 b sub 2 plus a sub 1 times b sub 1 plus a sub 2 times b sub 0, and keep going like this. Then general form given by this for the coefficient here, where the absolute value of g negative g0 is less than larger. So here, this rule is especially called the Leibniz rule. We just move to visit to exercise 6 here. Sorry, exercise 7. Here is typo. Exercise 7. Use mathematical